You know, you've used them to stick things to your fridge, and you've definitely seen them in movies lifting cars like they're nothing. Magnetism. It's a force we all kind of know, but it's also one of the most fundamental forces in the entire universe. It's shaping everything, from the tiniest atoms inside us all the way up to galaxies. So let's dive into this amazing invisible power. On one hand, you've got a simple little bar magnet, right? The kind you'd see in a science class. And then on the other hand, you've got this absolute beast, an industrial electromagnet, just casually lifting tons of scrap metal. It's the same fundamental force doing the work in both, just on a completely different scale. So what's the connection here? How is that even possible? And that, right there, is the big question we're going to answer. What is this invisible field that can reach out and act on things from a distance? And where in the world does it come from? The answer, as it turns out, is surprisingly simple, and it explains an incredible amount of stuff. So to really get a handle on the force itself, we first have to figure out what's producing the magnetic field to begin with. Where does this invisible influence actually start? Well, it really boils down to just two sources. First, moving electric charges. You run an electric current through a wire, you get a magnetic field. That's the basic idea behind every electromagnet. Now, the second source is a little weirder. Elementary particles, like electrons, they have their own built-in or intrinsic magnetic field. You can think of it as a property they're just born with, like their mass or their charge. And that is the secret behind every permanent magnet. All right, now for the main event. Because here's the thing. It doesn't matter if the field is coming from a current in a giant wire or from the tiny electrons inside a magnet, its effect on other charges is governed by a single universal rulebook. And here is the absolute key to understanding all of this. A magnetic field only puts a force on a charged particle if that particle is moving. If a charge is just sitting still in a magnetic field, it feels absolutely nothing. Zip, nada. Motion is the trigger. And this is it, the master rule that runs every magnetic interaction in the universe. Now, don't get scared off by the symbols, okay? This one little equation tells us everything we need to know. It says the force, that's F, on a particle is equal to its charge, Q, times this special operation called the cross product between its velocity, V, and the magnetic field, B. Now, that cross product thing sounds complicated, but you actually have a built-in calculator for it. It's called the right-hand rule. No, seriously, do it with me. Point the fingers of your right hand in the direction the particle's moving. Then curl your fingers toward the direction of the magnetic field. Whichever way your thumb is pointing, that's the direction of the force. It's like a little physics superpower you carry around with you. And for a negative charge, the force just points the opposite way of your thumb. Simple as that. So the most important thing to get from the right-hand rule is that the force is always pushing sideways on the particle. It's always perpendicular to the direction it's already going. And what that means is the force can't speed the particle up or slow it down. It can only change its direction. The best analogy is a tetherball. The string is always pulling sideways, forcing the ball to go in a circle, but it never makes the ball go faster. And this one simple fact that the magnetic force only changes direction, well, it has some absolutely profound consequences. It basically gives us the power to steer and control the subatomic world. And this image shows it perfectly. This is so cool. What you're looking at are actual electrons being shot into a magnetic field. That force is constantly pushing them sideways, acting like a perpetual turning force that bends their path into this perfect, glowing circle. This is not a simulation, people. It's a real photo of that master rule in action. You know, this ability to bend the path of particles isn't just some neat lab trick. It's how J.J. Thomson actually discovered the electron way back in 1897. He measured how much its path got bent. And it's the exact same principle we use today to steer beams of particles in massive accelerators, like the Large Hadron Collider, smashing them into each other to unlock the deepest secrets of the universe. So, we can steer a single particle. Got it. But what happens when you have a whole river of them, an electric current, all flowing together through a wire? Now that's where things get really interesting. Okay, imagine a simple loop of wire in a magnetic field. Current is flowing up one side and then it comes back down the other. If we whip out our right-hand rule, we can see the force on the left side of that loop is pushing upwards. But on the right side, where the current is going the other way, the force is pushing downwards. So you get an upward push on one side and a downward push on the other. And what happens when you push up on one side and down on the other? You get a twist, a rotation. This twisting force, scientists call it torque, is the fundamental principle behind every single electric motor on the planet. From a tiny fan in your computer to the engine of an electric car. All of it comes from that one beautiful, simple rule we just learned. And this brings us completely full circle. We've seen how a current can feel a magnetic force, but if you remember, we also said at the beginning that currents create magnetic fields. So let's connect those two ideas and finally understand the simple fridge magnet. So physicists have a way to measure the magnetic oomph and direction of a current loop. They call it the magnetic dipole moment. It's a fancy term, but you can just think of it as an arrow that shows how strong the magnet is and which way its north pole is pointing. Basically, any loop of current acts exactly like a tiny little bar magnet. Now look at this familiar pattern, iron filings around a bar magnet. And here it is, the big aha moment. What if this magnet isn't some single magical object? What if it's actually made of trillions upon trillions of those microscopic current loops? The electrons orbiting the atoms inside the metal, they are themselves tiny loops of current. And in a magnetic material, all of those tiny atomic magnets line up. They all point in the same direction, and their little fields add up to create the big, powerful magnetic field that we can see and feel. A fridge magnet is really just the collective voice of countless electrons all aligned and working together. So let's just recap this whole journey. It all starts with one simple thing: moving charges. There's a single elegant rule that governs everything they do in a magnetic field. From that one rule, we can see how we steer subatomic particles to do new science. We see how opposite forces on a wire create the twist that spins every electric motor. And we even see how the aligned motion of electrons inside atoms is what makes a simple fridge magnet stick. It all connects. It is just incredible. From one single equation, you get this rich, complex world of phenomena that literally powers our civilization. And it leaves you with a really fascinating question. As we get better and better at choreographing this intricate dance between electricity and magnetism, what new technologies are just waiting to be discovered? What's going to happen when we become even better masters of this amazing, fundamental force?